When we design AI systems, they often need to meet different requirements that cannot be all fully met simultaneously. Some of the requirements may be related to values like fairness, security, privacy, performance, and sustainability. Typically, we cannot optimize all these values at the same time. We must accept so-called trade-offs. But how do we decide which trade-offs between values are acceptable? And do we always need to make trade-offs? Or are there other ways for deciding between conflicting values? There are different ways in which we can deal with conflicting values, four of which I'll discuss here. First, we can take a calculative approach, where you try to calculate the best trade-off. Second, you can use satisficing, where you set the threshold for each value and look for an option that is good enough. The third urges us to rethink the values at stake and so find a solution. And the fourth, try to avoid trade-offs by technical innovation. To see these approaches in practice, we look at some examples of value conflicts and ways to handle them. First off, we can try to look for the best possible solution. A nice example for this is the trade-off between accuracy and explainability. As you can see, different machine learning techniques, from simple classification rules to neural networks, can be compared on two dimensions, accuracy and explainability. And generally speaking, we see that the most accurate methods, such as neural networks, are also the least explainable. So which do you pick for a particular problem? One way is to do a multiple criteria analysis. You can give the techniques scores for explainability and accuracy, and then calculate an overall score for each of them. We should then choose the one with the highest overall score. In this example, that would be a graphical model. The calculative approach seems straightforward, but it raises some questions. How do we determine the score of each alternative? This depends on your own judgment, but people may disagree about this. Another issue is whether the two values are equally important. We might add weights to the values, but again, how do we determine these weights? Another objection against the calculative approach is that sometimes a value cannot be traded off against another. For example, if we use AI in a legal context to make decisions in court, a minimal level of explainability might be required, whatever the accuracy of the algorithm is. And this brings us to the second approach, satisficing. Here we set thresholds for each of the values. In the conflict between accuracy and explainability, we might set the thresholds in this way. If we apply satisficing, we accept any solution that meets the thresholds. This means that we do not need to make a direct trade-off, but it raises also questions. How do we exactly set the thresholds? What if none of the options or many of the options meet the thresholds? How do we choose then? Thankfully, conflicts can sometimes be solved without using thresholds. The idea of the third approach is that value conflict is ultimately one between the specification of values. Take for example the conflict between privacy and fairness, where personal and potentially sensitive information is needed to calculate fairness metrics and to make an algorithm fairer. So, a conflict between privacy and fairness seems to arise. However, there are multiple ways in which we can understand the value of privacy. First, we can view privacy as confidentiality. If we understand privacy in this way, it's hard to see how we can avoid the conflict between privacy and fairness. If we collect the data needed for calculating the fairness metrics, they are no longer confidential, and hence we have a privacy violation. But alternatively, we might also understand privacy in terms of informed consent. The idea here is that privacy subjects, the persons to which the data pertain, that they can freely decide with whom to share or not to share the data. Data subjects have to give their informed consent. On this understanding of privacy, there might be no or lesser conflict in privacy. If data subjects know that personal data is used to increase the fairness of the algorithm, they might well be willing to share their data and there is no privacy violation. This becomes more likely if the developers can ensure that they will be the only ones who see the data. As such, value conflicts can sometimes be solved conceptually, as with privacy, or they can be solved technically. And this brings us to the fourth approach, called innovation. The conflict between performance and sustainability is a nice example here. As some of the most sophisticated machine learning techniques require a lot of computing power and therefore consume a lot of energy. High performance means lower sustainability, giving rise to a conflict. But in the future, we might find some clever technique or an algorithm that performs well without requiring too much computing power and thus less energy consumption. In such a case, technical innovations solve the value conflict. We have now seen 4 approaches for dealing with conflicting values. They each have their advantages and their disadvantages. The calculative approach gives you a best choice, but the calculations might be rather arbitrary and trade-offs might not always be acceptable. Satisficing gives you an option that meets minimal thresholds, but how do you set these thresholds? Respecification and innovation might be great, but they don't work for every conflict. Respecification may be impossible or unacceptable, and not every innovation solves a value conflict. It may even generate new ones.